This time, we're going to do some more work with systems, only now we're going to actually have three objects, but it shouldn't be a whole lot harder than before. So here's a quick summary of the problem. We've got a frictionless pulley here that has a rope connecting a 7 kilogram object to an 8 kilogram object. And there's a second rope, the yellow one, that's connecting the 8 kilogram block to the 3 kilogram block. And we want to know, what's the acceleration of the system going to be? Because we know the destinies of all three of these blocks are linked, right? What the acceleration of one will be the other one. So we want to find the acceleration of the entire system. And I want to know, what's the force of tension in the red rope? How much is that one being pulled on? And what's the force of tension in the yellow rope? And we'll see if they're the same and if things are expected. So right away, if you look at this thing and you think about what will actually happen, there's only two things going on here if you simplify it. There's the 7 kilogram block trying to pull everything down this way, and there's the 8 and the 3 kilogram that are both trying to pull everything down that way. And before we even do the problem, you probably know who's going to win. It's this side, isn't it? This side is going to win out eventually. So let's make the force diagrams and find out exactly what the numbers say. So if I treat this thing as one object, which means for now I ignore all of the ropes and I simply look at what the blocks are doing and I treat them sort of as one thing, then we've got two forces pulling it this way, which is the force of gravity on the red block, which is 80, and the force of gravity on the blue block, which is 30. And then going the other direction, we've got a force of gravity of 70. And as we know, this thing is going to be the one that wins. Well, how much does it win by? Well, if I total up the forces, then we get 110 newtons that are telling the system to go this way, and 70 newtons telling it to go that way, which gives us, very simply, a net force of 40 newtons going in this direction. Great. Well, now that we've got the net force, we know that we're ready to use Newton's second law, F net equals ma, to get to our first question here, what the acceleration of the system is. Now, when you use Newton's second law here, it's important to remember that the mass we're talking about is the mass of the entire system. It's all three of these blocks that are going to get accelerated by that 40 Newton net force. So for m, we've got to toss in an 18 here. So I get 40 equals 18a. With a little help from the calculator, I get 2.2 meters per second for the entire system's acceleration. Next, we've got to figure out the force of tension, how hard this red rope's being pulled on and how hard the yellow rope's being pulled on. And to do that, we need to stop thinking of it as a system. We use the idea of treating it as a system to find the acceleration, but now that we know that, now that we know the behavior of all three objects, we're going to start looking at them one at a time again. Let's start with the orange block. If I draw the force diagram on this thing, then immediately I get a downward force of gravity of 70 newtons because it has a mass of 7 kilograms. There's also going to be an upward force of tension from the red rope, and while we don't know what that is, we do know that it's going to be stronger than 70 because the orange block ends up getting accelerated upward. And we're going to have to use this 2.2 information to figure out exactly what this force is. So taking advantage of the information we already know, the acceleration, we can use Newton's second law on just the orange block to figure out that the net force on the orange block is 15.4 newtons. Now, if that's what the net force is, and there's a downward force of gravity of 70, then that means that the force of tension has to be 15.4 stronger than the downward force of gravity. So that's going to give us a force of tension of 85.4 newtons in the red rope. To find that out, I've got to look at something attached to the yellow rope. So I'm going to individually examine the red block. And immediately we have a downward force of gravity of 80 newtons. We also have an upward force of tension of 85.4 newtons because we already figured out what the tension is in the red rope. And we have a downward force of tension from the yellow rope, and that's what we've got to figure out here. Using Newton's second law, just like on the last one, I get a net force of 17.6 newtons, and we know that net force has to be down because on this side of it, it's going to accelerate downward. So the sum of the down forces is going to be this much stronger than all of the upward forces. If I set this thing up and I show that 17.6 is how much stronger the down forces are than the up forces, then it's just a matter of doing a little simple algebra to get a force of tension of 23 newtons on this thing, on the yellow one. And we're done. But as a final check, let me do the blue block just for fun. If I draw a force diagram for the blue block and I plug in that force of tension of 23 newtons, I end up with an acceleration that's roughly the same as what we started with. So it checks out and we're done here.